Welcome to Zaption Tour 7-6 Exponential Functions. There are 5 boxes, and for the 5th box we're going to use Desmos. So make sure that you have access to that because I'm going to show you some cool stuff on that. So let's dive right into this. Okay, let's talk about box number 1, the exponential function. The exponential function can be written as follows. It will have this form: y is equal to a times b raised to the x power. A times b to the x power. There's a couple of rules that we have to keep in mind. The first rule is that a cannot be the number 0. Hopefully you do realize that if it was the number 0, the entire equation would cancel out to just y equals 0, and that wouldn't give us exponential at all. The b value has to be greater than 0. We're going to talk about that in just a second. And the b value cannot be the number 1. Okay? The reason the b value cannot be the number 1, because 1 to the anything is just 1 power, so we don't get any exponential functions out of that. So we have a times b to the x. Okay? I want to go a little bit further for you. The a value, this is always considered your initial amount. Your initial amount. That's how much you start with, okay? The b value, this is the multiplicative factor by which you are multiplying that initial amount by. This is also considered the base of your exponential function. And of course, x is just the exponent. And it's the inputs. So I want to read this to you and see if this makes sense. Exponential functions model an initial amount, that's the a part that I was referring to, that is repeatedly multiplied by the same positive number. So this part right here, the same positive number, is referring to the b in the equation. The initial amount, this part right here, is referring to the a in the equation up above. So this is our form of an exponential function. It's y equals a times b, all raised to the x power. A cannot be 0. B has to be positive or greater than 0, and b has to not be the number 1. In box number 2, I'm going to introduce you to 4 separate graphs of exponential functions and what it actually means to be exponential. Right here, we're looking at the graph of y equals 2 to the x, and I want to explain a little bit about this graph. First of all, I want you to realize that this could be written as this: y is equal to 1 times 2 to the x power, where the 1 represents our initial amount a, the base is representative of a 2, and of course x is just the exponent. Okay, so all we're doing is starting with an amount of 1 and multiplying it by 2 repeatedly. The graph means this. I want you to make sure that we look at this, okay? If I draw a line, when x is 1, I go up to 2. When x is 2, I go up to 4. See that? When x is 3, I've gone up to 8. When x is 4, I've gone all the way up to 16. So that distance. The reason I'm bringing this up to you guys is because for equal growths of x, so when x goes from 0 to 1, I grew by a factor of 1. When it goes from 1 to 2, it grew by a factor of 4, right up there. Okay? Oh, sorry, this is 2, excuse me. The 0 is 1 right here. So when x is 3, I've grown by a factor of 8. Okay? When x is 4, I've grown by a factor of, I've gone up to 16. So each of these right here, I got 2, 4, 8, 16, are just repeated bases of the number 2, right? 2 to the first is 2, 2 squared is 4, 2 to the third is 8, 2 to the fourth gives you 16. So what you want to keep in mind is for equal spacing of x values, you get equal factors of growth. That's what it means to be exponential. Equal spacing of x gives you equal factors of growth. Okay, so this is the example of 2 to the x. I have a couple more. This is the example of negative 2 to the x. Okay, I want you to keep in mind that that can be rewritten as y equals negative 1 times 2 to the x power. So our initial amount is now negative 1. Our base is still 2, so we're still adhering to the same rules as up above. The only difference that the negative 1 out in front does is it gives us a reflection over the x-axis. So you might want to make a sketch of these graphs right here. Pause the video and make a sketch. Okay? So regular 2 to the x is exponential growth. As x grows, my function grows. This represents another exponential function too, but I'm falling, right? As x grows, I get lesser and lesser. So the only difference here is that if I have a -1 out in front, I get a reflection over the x-axis. I've got 2 more for you. Okay? This is y equals 1/2 to the x power. Again, this can be rewritten as y equals -1 times 1/2 all to the x power. Or not -1, excuse me, +1 times 1/2 to the x power. This is still your a amount. This is still your b amount, so we're still adhering to the same rules. And again, the same rules apply, right? So if I'm at -4, I'm all the way up at 16. If I increase x1 value, I have now decreased by half as much. This was 16, now I'm up to 8. Again, if I increase my x value, I have decreased by half as much. If I increase my x value, I have decreased by half as much. This is exponential decay because I am decreasing by the same amount for equal spacing of x values. The final one is I'm going to put a negative in front of that, and you guessed it, it just reflects it over the x-axis, or at least hopefully you guessed it. And again, this can be rewritten as y equals -1 times 1/2 all to the x power. So all I get is that negative out in front. The whole point of me showing you this is that gives us a reflection over the x-axis. Okay, but again, if I'm at -4, I'd be down here at -16. Okay, if I increase x to one spot, I have now grown, or I have cut my output in half. Okay, so I've gone from -16 up to -8, and then -8 up to -4, and so on and so forth. Okay, so this is what it means to be exponential. In box number 3, I want to explain the difference between identifying a linear function versus an exponential function by looking at a table. On the left-hand side, in yellow, this is a linear function. On the right-hand side, in blue, this is an exponential function, and I want to talk about the difference between the two of them. First, let's consider the x's. In here, okay, going from 0 to 1, from 1 to 2, and from 2 to 3, notice that I'm just increasing by 1. So +1, +1, +1. Okay? Same thing over here. Going from 0 to 1, I increase by 1. 1 to 2, I increase by 1. 2 to 3, I increase by 1. Okay, so that is the same in both of them. Okay? Now I want you to consider the y values. So let's take a look at this. If I go 0 to 3, I have a difference of 3. Okay? If I go from 3 to 6, I have a difference of 3. If I go from 3 to 9, I have a difference of 3. Okay? So I could consider the x values have a difference of 1 and the y values have a difference of 3. If both the x and the y's have a difference of the same value, 3 for the y's, 1 for the x, then this would be considered linear. Take a look at that in the exponential as well, though. Okay, 1 to 3, that has a difference of 2, doesn't it? 3 to 9, well, that has a difference of 6. And 9 to 27, again, this is not constant, okay? So this does not have a common difference, but it does have something, right? If I take 3 and divide it by 1, I get a value of 3. If I take 9 and divide it by 3, I get a value of 3. If I take 27 and divide it by 9, I get a value of 3. Or similarly, 1 times 3 gives me 3, 3 times 3 gives me 9, and 9 times 3 gives me 27. So what we look for here is the common ratio. Okay? So in this case, you can see that the ratio is a factor of 3. I'm just dividing the term by the previous term. Over here, the difference is what's the constant, and that is how you tell the difference between the two. A linear table, for equal values in x, you will get the same difference in y. On an exponential table, for equal values of x, you will get the same ratio of y's. In box number 4, I'm going to show you how to graph an exponential function. So we're going to graph the function y equals 3 times 2 to the x. And we're going to graph it by making a table. Okay, I want you to notice that the a value is 3 and the b value is 2. So what we're going to do is we're just going to simply plug in. So here we go. So I'm going to do 3 times 2 to the negative 1. Well, remember, 2 to the negative 1 is the same thing as 3 times 1/2, right? 1 over 2 to the positive. So therefore, I would get 3 halves out of this thing. So I would have negative 1 comma 3 halves. Okay? So at negative 1, I'd be up at 1.5. So that's the same thing as 3 halves. So I'd be right about here. That's my first point. Okay? Plug in a 0. I would have 3 times 2 to the 0. Gives me 3 times 2 to the 0 is 1. So that'll give me a value of 3. So I'd have 0 comma 3. So 0 comma 3 would be definitely on the graph. Plugging in a 1, I would get 3 times 2 to the first. That would give me just, well, 2 to the first is 2 times 3 is 6, right? So I'd have 1 comma 6. So over at 1, I'd be up here at the number 6. For 2, I would have 3 times 2 squared. That would give me 3 times 4, which would give me a value of 12. So I would go over to 3 and go up to 12. And, oh, sorry, 2, 12. There we go, right there. And finally, plugging in a 3, I get 3 times 2 to the third. 2 to the third is 8. 8 times 3 is 24. So I'd have 24, so I'm off the chart right there. Okay? So I would have something that would be looking like this. I come up and go up like this and go up, and it would keep going on forever and ever. Okay, in box number 5, last box, I'm going to show you how to solve one variable equations using your graphing calculator or Desmos. We're going to do the graphing calculator part in class, so today I'm going to show you how to use Desmos to solve this. So I want to solve 2 to the x equals 0.5x plus 2. So what I'm going to do is I'm going to break this up into 2 equations. I'm going to break this up on the left-hand side and break it up on the right-hand side. So I'm going to have y equals 2 to the x be one of my equations, and I'm going to have y equals 0.5x plus 2 be my other equation. So I have these 2 separate equations, and I want to know when they are equal. So I'm going to go over to Desmos, and I've already plugged these in. I have y equals 2 to the x, and I have y equals 0.5x plus 2, and I'm going to turn both of them on and graph them. Okay? Now when you're in Desmos, if you just click on the line and then click, you can see these gray dots show up. You can click on exactly where the 2 points cross. So if I click on that one, the red one, I can click that. I can see exactly where the 2 points cross, or the 2 lines cross at that point. We're looking for the x value. So I take a look at the x coordinate for each of these. So this one will be negative 3.863. And this one would be 1.445. So there are my 2 solutions, because that's the x value that would give me an equal amount on both sides of that equation. So negative 3.863 and 1.445 would be your answers. So I go back over here. So negative 3.863 and 1.445 would be your x equals both of those. We'll do more of those in class, but that's the breakdown so far.